And actually, there's more powerful attacks. There's this mind-melting, incredibly clever, brilliant idea called return-oriented programming, which says, I could take return into libc, and I can get more than one. I can get as many as I want. So let me tell you about return-oriented programming, because this is an attack that is used in the wild frequently, and is this brilliant generalization of return into libc. And the idea is, we're going to do this many times. We're going to repeat this whole idea many times instead of just once. And we're not going to be limited now to just what we can find as library functions. We're going to go look around in the code for a gadget. And by a gadget, I mean a short sequence of instructions. A single gadget is a short sequence of instructions. And we're going to try to find a way to piece together multiple of these gadgets. I want these 2 instructions here, these 3 here, these 2 here, and if I could get them to execute in that way, then my malicious payload, the malicious effect would be triggered. Okay? So the ROP attack creates this chain of gadgets. Each gadget is from existing code somewhere in the address space. And then the effect of the exploit will be to execute those in that sequence. And the way the attacker is going to arrange to execute those is by doing something like a return into libc. They're going to overwrite the call stack so that the return address that they overwrite points to the first gadget. And if we arrange it, that gadget doesn't need any arguments. If that gadget is so simple that it just does some stuff and then returns, it's going to then pop off and look one above that to figure out where to go next. So we put in the spot where it's going to look, the one above that, the address of the second gadget. And that second gadget's going to, if it has no arguments and just like adds to a register or something and then returns, well, it's going to pop off and go one above that to figure out what the return address is. So we put in that one above that, we put the address of the third gadget. So we fill in the call stack with the addresses of all of our gadgets, and then it's going to just go right through all the gadgets. Okay? So now we got to get lucky to find gadgets that, when put together, cause the effect we want. And here's just the amazing thing, which is if you go trawl around all of memory, you can find lots of gadget. And typically, a typical gadget would be something really simple. It does something really trivial, like add 1 to EAX and then return, like 2 instructions. Or multiply EX by 3 and then return. Or, if EAX is positive, do one thing and then return. Okay? So each one of those is a very simple operation. But you can think of it as like 2 or 3 instructions. So it's a sequence of, 5 or 10 bytes or something you're looking for. So you go look through all of the existing code memory, and do you see that sequence of 5 or 10 bytes anywhere? Could be those 2 instructions were something in the middle of a function, and so I reuse that. It could be that they're not present anywhere in the binary, but if I start overlap in the middle of some existing instruction and interpret the bytes there, then those happen to be the sequence of bytes that would be interpreted as the gadget I want. So you trawl through all of code memory to find all the gadgets you can find. You put together what the effect of each one of those is, and if you get lucky, and it often turns out that for most real-world applications there's enough code that you get lucky, that there's enough of these operations that you put them all together and you've got something Turing complete. You got something you can add one, you get something to multiply, you can do a branch, you could do this, you can do that, and before you know it, this combination is Turing complete, and so that means that you can compile anything you want to do into a long sequence of gadgets. Okay. And you can go download tools that will do this for you. They're called ROP compilers, because they're just compiling to this crazy language of gadgets. It will go find the gadgets that are present and figure out how to compile your malicious payload into that sequence of ROP gadgets. Okay. So this completely hoses non-executable pages. It's just dead in the water once you know about this kind of ROP stuff. And it sounds incredibly difficult, and it is if you're the first person to write the ROP compiler. But what you see is this kind of standard trend in security where this brilliant, complicated idea, first starts out as someone's blog post or research paper. In this case, this brilliant research paper that then somebody implemented, and the next it's implemented by national security agencies, and then before you know it, it's open source code that anyone can use and script kiddies are using. Okay, so today ROP attacks are very feasible, and they make, if all you used as hardening was non-executable pages, you would discover that it's not actually secure, because all the attacker has to do is convert their payload into a ROP chain, and they're golden.
Wow.
Yeah. Wow.
Is the stack usually large enough that you wouldn't just write out?
stack's usually big enough that, you need kind of a lot of gadgets, but maybe it's in the hundreds. It's not in the millions, so you're probably fine. Yep. How do you get the address of a function in libc? Well, you'll see in Project 1 that if there's no particular defenses in place, you run the same program twice, and often everything's at the same address. So how do you do that? Download your own copy of the application. Make sure you install the same as your victim's machine, same version of the operating system, same architecture, same libraries. Then run it on your own machine and look what address it's loaded at with a debugger.